Okay, welcome to the functional and witness encryption session. We have 4 talks in this session. The first talk is multi-client functional encryption with the fine-grained access control by Ki Gwen, David Poinsable, Yu Hugh Wang. Ki is going to talk.
Hello. Thank you, Rio, for the introductions. Can you hear me well? Yes, so my name is Ki, and today I would like to present our work on multi-client functional encryption with fine-grained access control. So this is a joint work with Yung Hữu Phan and David Pashawan. Okay, so first I will give the motivations and the context of our paper, and then the related works in the literature followed by our contributions. And in the second part of the talk, I will give some technical overview of our constructions and some high-level technical ideas. So the starting point is the all-or-nothing nature of a public key encryption. That is, given a secret decryption key that you decrypt and get the whole plain text or nothing. Later, there is the notions of attribute-based encryptions that give some control. If the policy in the key is satisfied, then you can decrypt and get the plain text, else nothing. And more than a decade ago, there is the notion of functional encryptions, in which you control the quantity of information leaked about the plain text through the function evaluation. However, one observation is that on these secret decryption keys, their usage can be unlimited in the way that the decryptor can use them in whatever way he wants. And in this work, we focus on functional encryptions in the multi-user setting. So there are 2 main notable notions, that is the multi-input and the multi-client. So there are various notions of multi-input. So, but in this work, we consider them to be the FE schemes where the plain text can be encrypted component by component, and the components can be combined arbitrarily using a functional decryption key to get a functional evaluation. On the other hand, there's also the notion of multi-client functional encryption. That is, there are multiple clients in the system. Each of them has their own private encryption key, and they can encrypt the individual data independently under some specified tag, which can be some timestamp metadata, for example. And in the end, a functional decryption key allows combining all the ciphertext components only if all the partial ciphertexts are encrypted using the same tag. So this limits the absolute combinations resulted from the MIFE, for instance. And the problem with the unlimited usage of the encryption keys still persists in this setting. So our goal is to enforce some fine-grained control over the decryption keys. That is, we associate a policy in the key, and at encryption time, each client in the MCAV setting will encrypt their partial ciphertext under some specified attributes. And only when on client's attributes satisfy the keys policy, we will be able to obtain the function evaluation on the combined plain text. Otherwise, we obtain nothing. In particular, in this work, we consider the function class that allows computing inner products, and the asset control can be expressed using linear sequencing scheme or LSSS, for example. One remark is that this MCFE with fine-grained asset control can be captured by the general notions of MCFE if the class of functions can express the asset control. So one might very well wonder why MCFE, why we focus on the multi-client version. So first of all, in our particular constructions for inner products and LSSS, we treat the tag by hashing them. And so if we fix and publish this hash value, the notion of tag becomes somewhat transparent, and we obtain an MIFE scheme. On the other hand, in the other directions, given MIFE or inner product with LSSS, if we want to obtain an MCFE scheme, because in the MIP, there's no notion of tax whatsoever. So we need to include some equality check for the tax. And it turns out to be infeasible in this case for this particular function class to compute inner products and with the LSSS asset control. Even in the case of simple policy like identity base. And I refer to our paper for more details and discussion on this technical point. So therefore, our goal now becomes constructing MCFE schemes to compute inner products with the asset control using linear secretary scheme. In the literature at Asiacrypt 20, Abdallah et al. Studied this problem of FE plus asset controls. And they propose several candidates using pairings and learning with errors, where the asset controls can be expressed using monotone span programs. In the end, they gave also a generic transformation from single clans FE scheme to MIE scheme with adaptive security and quadratic total communication. In this work, we study this problem in the setting of MCFE, where the asset control can be expressed using linear secretary schemes that can be identified with the underlying model span programs. And we obtain adaptive security in the random oracle model and linear total communication. And as I've mentioned earlier, we can deduce an MIA scheme by fixing and publishing a hash value, and while preserving all the advantage regarding the security level or the total communication. So let's move on to the formal definitions of MCFE with a parent asset control. So the asset control is expressed using a relations between key policy and the attributes put inside the independent and separate components by end clients. So there exists an authority given the function description and the policy. We output the key corresponding to this policy and the functions. And all clients, each of them having their private encryption key. We use the key to encrypt the partial ciphertext. And the correctness requires that only when all client attributes satisfy the key policies, we will be able to obtain the function evaluation. Furthermore, about the security model, is an interactive security game between an adversary and a challenger who picks a random challenge bit. The adversary is allowed to query for multiple times functional decryption keys corresponding to policies and functions of his choice. Moreover, in this testing of multi-client functional encryption, there are multiple clients. Each of them has the private encryption key. Therefore, the adversary is also able to corrupt a client and receive the corresponding encryption key for multiple times. And the adversary can also demand the challenge ciphertext for two challenge vectors x0, x1, component by component, under some specified tag and attributes to receive the challenge ciphertext. So furthermore, we restrict that the adversary can only use one challenge tag, but we allow him to query an encryption oracle to encrypt data of his choice for arbitrary clients, and he can do this multiple times. So using a standard hybrid argument, this is equivalent to the multi-challenge notion. And in the end, the adversary outputs a guess for the challenge bit. So we can have various weaker notions by restricting the adversary to declare upfront the challenge queries or the corruption queries. And moreover, in this security model, the functional keys might allow the adversary to decrypt the challenge ciphertext. And therefore, if this is the case, we constrain that the two inner products of the two challenge vectors must be the same. So before going into the technical overview, I recall some technical tools that we use. So maybe the dual pairing vector spaces introduced by Okamoto and Takashima. So we're in a prime order bilinear group written additively. And we consider some basis matrix of scalars with some public row vectors and private row vectors. So we take it inverse and then transpose to get the dual basis. And we raise these two bases into the corresponding groups, G1 and G2. We get two matrices of elements in G1 and in G2. So these are called the dual bases of the dual pairing vector space. And given these two matrices, we can have some notion of vectors of elements and define their products by simply taking the pairings component by component and adding up together. So in the end, the result is an element in GT whose exponent is the inner product of the two underlying vectors. So being equipped by these tools, let's move on to a single client scheme. So there is only one client, and the ciphertext consists of multiple ARS ciphertext that is from the celebrated in the product functional encryption by Juan Liebeck and Stelle. Moreover, for the asset control part, we have a vector C0 in the basis H containing the randomness for the AOS ciphertext as well as the asset control. And for each attribute needed in the ciphertext, we have a vectors in the basis F. On the other hand, in the key, we use the AOS to secretly share a random secret A0 put in K0 star to mask the AOS key. And for each attribute, we have a vector K at star in the basis F star. So by using the linearity of the product operations between vectors, we're summing up the products over attributes in a reconstruction set for the AOS, for the AOSSS. We will have psi times I0 in the exponent of GT. And we can recover the unmasking value of the AOS decryption procedure. And in the end, we can recover the inner product of X and Y using the usual AOS decryption. So about the security, we perform using a game-based proof where the changes are done by basic change in the DPVS framework. And the main idea is to embed a newly generated secret pairings of another A0 prime secret in the ciphertext and the keys vector and masked by some random values. Yeah. So some subtlety is that in these scenarios, we can be in two cases where the key can decrypt the channel ciphertext. And in that case, we can apply some ABA techniques such as the dual system method. Or it can decrypt the channel ciphertext, but we constrain that the delta X in the product with Y, where delta X is the difference between the two channel vectors. This inner product must be 0. And in the adaptive security setting, we want to know which case we will be in the course of simulation. So our main idea is if this inner product is non-zero, then this key cannot decrypt the channel ciphertext. And therefore, we embed term by terms the delta xi times yi along with the secret sharings in the key and the ciphertext for both the attribute vectors and the C0, K0 vectors. And in the end, thanks to these secret sharings and the random mask set, we can randomize the A0 prime to a newly A0 prime independent secret that allows us to modify the channel ciphertext to be independent of the channel bit. And finally, because we need to embed term by terms the inner products of delta X and Y, we will need at least n coordinates in the key and ciphertext vectors. And therefore, the ciphertext size increases to linear in n. and also depending on the number of attributes needed. In particular, if we are in a non-trivial, simple asset control identity based, D can be equal to 1, and we obtain something linear in N. And more details can be found in session 5 of our paper. So that's for the single client. Towards the multi-client, we use technical ideas that we call compress and duplicate. So namely, if we naively duplicate all the formats of the key and the ciphertext vectors from the single client to the multi-client, then we will have something quadratic in N, because the vectors are already of size linear. So the main observations is that we can compress the attribute vectors into the same basis F star and F for all clients, thanks to the indexing technique in DPVS, also introduced by Okamoto and Takashima. And each client I will be embedded the newly secret shares together with YI only. And we do not need to accommodate all the N terms in one single vectors anymore. And the same thing can be done for the K0 and C0 vectors, where we duplicate the HI and HI star for each client. And then each client I deal with the terms YI times delta XY, delta XI. And we obtain a constant auxiliary number of coordinates for each client and each attribute if needed. And in the end, the total communication reduces to linear in N. So I refer also to the session 5 of paper for more details on this technique. And to conclude, we propose MCP candidates to compute inner products with asset controls using linear secret-sharing schemes, achieving adaptive security in the random oracle model and linear total communications. And the latter is thanks to the compress and duplicate, which is a technical idea we developed along the process. Thank you for your attention.
Are there any questions? We have plenty of time for questions. Okay. So I didn't see why do you need the random oracle model? Why do you need hash? Or so is it crucial for achieving adaptive security or compressing communication complexity?
Both, because we use the random oracle to hash the tag and derive the randomness to put in the ciphertext.
So
yeah,
okay. So from the to deterministically generate common randomness from the tag. Okay.
Yes.
I see.
And in the literature, there also exists works on MCFE that does not require random oracle and is using AWE techniques and not the pairing based.
I see. Thank you. Any other question? No. Okay, then let's speak again.
Thank you.
The next talk is compact FE for unbounded attribute weighted sums for log space from SXDH by Pratish Datta, Tapas Paul, Katsuki Takashima. Tapas is going to talk.
Thanks, Ms. Mukesh, for the introduction. I am Tapas, and I will present our paper, Compact FE for Unbounded Attribute-Weighted Sums for log space from SX stage. It's a joint work with Potish Datta and Katsuyoki Takashima. So in functional encryption, we have a setup authority who generates a master public MPK and a master secret key MSK. Using MSK, the authority can compute a secret key SKF corresponding to any arbitrary function F and distributes it to the users of the system. Using MPK, a data owner can now encrypt messages and publishes the ciphertext CTM. The user now decrypts CTM using SKF and learns the functional value of the message. The simulation security is the most desired notion of security, at least according to the literature. So it roughly says that given a set of secret keys, SK1, SK2, SK3, so on, the adversary can only recover the functional values of the message M and nothing else about the message M from the ciphertext CTM. In this work, we consider adaptive simulation security, and it is formalized by the following set of algorithms. So here, pre-challenge secret keys are generated using a simulated master secret key MSK star, and the challenge ciphertext is computed using MSK star and state ST, which contains functional values of the message M that are queried till then. The adversary can also query post-challenge secret keys, and these are answered using the functional values of the message M. And we say that FE is adaptively simulation secure if these two sets of algorithm are computationally indistinguishable. So simulation security can also be classified into bounded or full collision resistance setting. In bounded collision resistance, adversary is only restricted to query a bounded number of secret keys, whereas full collision resistance setting gives the adversary of full freedom, where he can query any polynomial number of secret keys both before and after the challenge ciphertext. So FE has been constructed for general class of functions, for example, Turing machines or all circuits. However, these constructions are mostly inefficient and or impractical. These are bounded collision resistant, and security can be based on heavy cryptographic tools such as indistinguishability obfuscation or sub-exponential security of LW. So as a result, community also focused to build FE for specific class of functions, for example, linear, quadratic functions and their variants. And these constructions are efficient, simple, they are full collision resistant, and the security can be based on simple and standard assumptions such as DDH, K-lin, or LW. And more importantly, these constructions can be deployed in practice. So this work focuses to advance the FE for specific class of function, namely attribute-weighted sums, introduced by Abdallah, Gong, and Wu. So here we generate secret key corresponding to a function f, which takes input a vector of length m and outputs a vector of length n. And message consists of a tuple x and z. Here we call x as public attribute and z as private attribute. The functionality outputs in a product between two vectors, fx and z. So the state of the art for AWS, consider function class to be only ABP or arithmetic branching program. Master public key size depends on both x and z. Ciphertext size depends on z. Although the first work of the later consider only semi-adaptive simulation security model, which is a little bit weaker than adaptive simulation model. We last year showed that how to achieve adaptive simulation security for AWS, but now ciphertext size depends on both x and z. And why this AWS is interesting? Because it has many applications in the sense that it already captures existing important FE schemes such as IPFE or inner product functional encryption, ABE or attribute-based encryption, AB IPFE or attribute-based inner product functional encryption. However, the current structure of AWS has several limitations. So it is defined in non-uniform or non-dynamic model. Setup is kind of bounded. That means master public key size not only depends on security parameter lambda, but also both on x and z. And ciphertext is also not input specific. As a result, it captures only bounded FE schemes such as IPFE, ABE, where functions takes input of bounded length. So let's see how we can remove these limitations one by one. So we can consider uniform or dynamic modular computation. For example, function class can be Turing machine. Here, attributes can be added or deleted at any point of time. Setup could be made unbounded. That means master public key size only depends on lambda, which is the security parameter. Ciphertext size can be input specific. And with all these, we can also have adaptive simulation security. So this is exactly our work. And due to the feature of uniformity, we now capture unbounded FE schemes such as unbounded IPFE or unbounded ABE, etc. So in summary, we define FE for unbounded AWS or UAWS, and we construct it for log space Turing. And our construction has several exciting features. For example, it has compact ciphertext, meaning that it will not grow with respect to multiple occurrences of a particular attribute in the weight function. Also, our scheme is full collision resistance, and it achieves adaptive simulation security under well-known SS stage assumption. So let's see how to define FE for UAWS. Here we first note that setup only depends on security parameter lambda. Function is a tuple of Turing machines MK, where K runs over an index set I. Message is a tuple of X and Z. Here X is a binary string, and Z can be any vector of arbitrary length. So for example, let's say N. The functionality outputs sum of MKX times ZK, where K runs over I if I is a subset of box N. And as previous, we have X is public and Z is private. So as a toy example, if your index set I is 1, 2, and 4, and Z has length 5, then the functionality outputs M1X times Z1 plus M2X times Z2 plus M4X times Z2. Okay, so technically we started from a very nice work of Lin and Luo, where they build the primitive of ABE for circuits and Turing machines from IPFE and arithmetic key garbling scheme, in short AKGS. Last year we showed that how to extend their framework from payload hiding to attribute hiding setting in the context of FE for AWS. And now we further extend the framework from non-uniform model of computation to uniform model of computation by adding the feature of unboundedness. So in particular, we use AKGS for Turing machines from LL20, and we also use index encoding mechanism with IPFE, and we devise distributed randomness mechanism to achieve our goal. In the pathway, we first construct one key, one ciphertext secret key FE for UAWS, and then extend it to FE for UAWS in public key setting. In this talk, I will mainly focus on this one key, one ciphertext version of the primitive. So IPFE is an important tool of our construction. Here, function and messages are vectors, and the functionality outputs inner product between the vectors. In this work, we consider IPFE with pairing E, G1 cross G2 to GT. Here, function and messages are encoded in the exponent of the source group G2 and G1, and the functionality computes the inner product in the target group GT. The function hiding security of IPFE says that two sets of secret keys and ciphertext are computationally indistinguishable if inner product between the vectors for the two sets are equal. And AKGS is another important tool. AKGS over ZP is a protocol between two parties. First party garbles a function f with values z and beta and outputs a set of level functions L1 or LT. Second party, given fx and level values at input x, efficiently computes zfx plus beta. So here we want that f and x to be public and z and beta to be private. And this is formalized by a simulator which, given fx and the output value zfx plus beta, simulates the level values L1 or LT. AKGS has a nice property of linearity, which tells that eval is linear in the level values L1 or LT, whereas the level functions are linear in the input x. We consider AKGS with piecewise security, and it has two properties. First property says that given level values from L2 onwards, we can reversely sample the first level value depending on the output value zfx plus beta. The second property says that given level values from L3 onwards, we can replace the second level value with a uniformly random value R2. And it can be continued till the last level. This property is named as marginal randomness, and marginal randomness together with reverse sampleability is called piecewise security. And it is very easy to see that piecewise security implies normal simulation security. Okay, so before going to our construction, let's see the core idea of DP21 for building FE for AWS for ABPs. So for this talk, I consider a simple version of function input and output. Function consists of two ABPs, F1, F2. Input is X and Z, where Z has length 2, and output will be Z1 F1X plus Z2 F2. So in key generation, F1 and F2 are first garbled with Z1 beta 1 and Z2 beta 2, where Z1, Z2 are treated as variables. The garbling algorithm outputs some set of vectors V, where Vk represents the level function cell k for k less than t, which depends on input x, and Vt represents the level function Lt, which is a function of either Z1 or Z2. Accordingly, we consider two IPFE, one for computing the level values for k less than t, and other is for computing the level value for t. The key generation algorithm finally outputs IPFE secret keys corresponding to all these V vectors. In encryption, we first compute IPFE secret ciphertext CTX corresponding to the vector 1, x, and we also compute two IPFE ciphertext CT1, CT2 corresponding to the vectors 1, Z1 and 1, Z2. In decryption, we first employ the IPFE decryption algorithm to get the level values L1.LT corresponding to the function F1, and then given F1x, we can employ the evaluation algorithm of AKGS to get the output of Z1 F1x plus beta 1. Similarly, we can get Z2 F2x plus beta 2. Now, these two values can be added to get the final result of Z1 F1x plus Z2 F2x, given the fact that beta 1, beta 2 are secret shares of 0 to hide the partial decryption result. Okay, so keeping this idea in back of our mind, let's see how we can construct FE for AWS for two dimensions. So these are the general form of function input and output. However, for this talk, I only consider a simple version of function, which consists of two dimensions, M1, M2. Input is X and Z, where Z has length 3. And according to the functionality, we'll get an output of Z1 M1X plus Z2 M2X. Okay, so as previous, we want to garble M1, M2. However, we note that AKGS for ABP will not work here because M1, M2 are two dimensions. So we go for AKGS for two-dimensional computation. And let's see how it works for DFA for concreteness. So in deterministic finite automata, we have a set of states, 1 to . One is the initial state, and although we can have many accepting state, but let's consider only one accepting state, Q accept, and in this example, it is 3. In DFA, we also have a transition function delta that defines a map by reading the input bits of the DFA. DFA can also be imagined as a layered branching program. Here, each layer consists of 3 nodes for this toy example. And we have a total of n+1 layers if we consider a input length of n. The edges between the layer j and j+1 are defined by the transition function delta. And since delta is fixed, so we have the same set of edges for each pair of adjacent layers. We can also consider matrices M0, M1 corresponding to the bit 0 and 1. And we traverse from layer 1 to layer n+1 using this following matrix multiplication. Here E1 indicates that it is a first basis vector, and it indicates that we always start from initial state 1. So after we read the n bit of inputs, we multiply it with another vector EQ accept, which represent the accepting state. And finally, we'll get an output of 1 or 0 if the DFA, depending on the DFA accepts the input or not. So therefore, we want to garble Z mx plus beta, where mx is this matrix multiplication. So let's consider one bit of input, then it can be garbled using the following equation. Here, by sampling random vectors R0, R1. And L0, L1, L2 are the level functions, where L2 depends only on the private input Z. If we extend the input length, then we can actually extend the chained equation by sampling more and more random vectors. So for example, if we have n bit of inputs, then the total size of garbling will be nq plus 1. So now let's say we want to apply this strategy into our setting. However, we now see that then we need to generate NQ plus 1 many level functions at the time of key generation. However, n is the input length and we do not have it yet when we generate the secret key. So let's look at the qjth level function in a bit more detail. So recall that we sampled many random vectors r0.rn, and each of which has length q. We can represent this matrix by a tensor product between two vectors. And these vectors Rm and Rx can be sampled independently. In particular, we want to write Rj to be Rxj times Rm, where Rxj denotes the jth entry of Rx. So this helps us to represent LQxj as inner product between two vectors. One is known to the encryptor and other is known to the key generator. Let's call these vectors as uj and vq. We can similarly represent L0 and the last few level functions LQj. So basically, we distribute the process of garbling between key generator and encryptor. So using this idea, we can now directly encode these Turing machines into some V vectors and then generate IPFE secret keys. In encryption, we encode X and Z in some U vectors and we compute IPFE ciphertext. And decryption works as before. However, this simple scheme in this slide is not secure. To see this, let's look at two important steps of the security analysis. So in the first step, we use reverse sampleability to reversely sample L0I depending on the output Zi minus X plus beta I. And if the secret key is queried before the challenge ciphertext, then we hardwire this L0I in U0 vector. However, we notice that we do not have enough space to place these L0I values for all I. And in the second step, when we try to randomize the other level values LJI for j greater than 1, we do it through the uj vector. And again, we do not have enough space. So what we do, we make multiple copies of U0 and uj depending on the length of z, right? But it opens door to a mix and match kind of attack. Now adversary can compute inner products between vectors related to the Turing machine M2, M1 with vectors related to the input G2 and vice versa. And it will help the adversary to compute an unwanted output Z1 M1X plus Z2 M1X. So to tackle this, we apply index encoding mechanism. So we encode the indices and append it to all the vectors in such a way that if you take inner product between the vectors having the same index, we get a meaningful result. Otherwise, we will get a garbage value. So this prevents mix and match kind of attack. And we hope to get the correct output. So let's see how we can actually use index encoding mechanism in this security analysis. So recall that we need to hardwire L0I in U0 vector. And this can be done using function hiding security of IPFE. Now let's say we have one more Turing machine M4 into the function M. So the inner product between the encodings rho minus 1i dot pi 44, 1 will not be equal to 0 for I equal to 1, 2, 3. Here 1, 2, 3 means the indices of the input Z. And this additional entropy will be provided by index encoding technique. Using the function hiding security of IPFE, we can now sample beta 4 independent of beta 1 and beta 2. And this makes sure that beta 1 plus beta 2 plus beta 4 will not be equal to 0 with high probability. Therefore, the adversary will not get the output Z1 M1X plus Z2 M2X for such a function M. Right. So in the next step, what we want to do, we try to randomize the other level values, LJI for j greater than 1. Recall that these vectors are encoded in the power of source group because we considered IPFE with pairing. As a first step, we bring the partial garbling randomness into the UJI vector using the function hiding security of IPFE. And then we again recall that this Rj minus 1 is basically Rxj minus 1 times Rm. And in the next step, we hope to use DDH in G1 to replace all these Rj-1 by Sj-1, which are uniform, random, independent of Rj-. However, to apply this step, we need to make sure that Rxj-1 and Rmk are encoded only in the exponent of G1. Unfortunately, it is not the case because Rmk may appear in VQK, which are encoded in the source group G2. For any K, it will appear, right? Hence, we cannot apply this DDH in G1 in this fashion. So here we devise distributed randomness mechanism, which works well with the framework of UAWS, and it eventually helps us to randomize these level values, LJI, with uniformly random values. And we can do it for other vectors that encodes the private input Z. Okay, so the actual proof is much more technical for this, and also for the full-fledged FE scheme, I refer to our full version, which is available at the event. Okay, so I will conclude my talk with a few open problems. So it will be interesting to see a construction of our FE for UAWS with succinctness. Means that ciphertext size will only depend on the private inputs, not on X. And also, it will be interesting to have such a scheme with adaptive simulation security. And the next open problem would be to have FE for UAWS from lattice-based assumptions such as LW. Yeah, thanks for your attention.
Are there any questions? We have plenty of time for questions. So, so this is for log space, right?
Yeah.
So, but in the building block, you use AKGS for Turing machine. So Turing machine, but means the log.
Yeah. We have used AKGS computation for log space Turing machine.
Log space Turing machine. Yeah. So it is infinite.
Yeah. It is implicit in that AKGS. That's constant. Yeah.
Any other question? So I have another question.
Yeah.
So this is based on pairings, right? What is the technical hurdle for achieving from lattice-based assumption?
Yeah, I mean, you mean that from LWE, maybe the main problem would be to design the framework of DPVS or function hiding IPFE with LWE.
Okay, so it is maybe I missed something. So it's in general pairings is useful for achieving adaptive security, but here also useful for functionality or for this kind of FE.
Yeah. I mean,
so even if we do not consider adaptive security, is it hard to achieve this kind of FE scheme from LWE?
Yeah, I think so, because we used, I mean, we need function hidings property of IPFE, even if we consider selective security, right?
Okay.
So that's why I guess it will be hard.
Okay, I see. Thanks. No question? Okay, let's thank the speaker.
Thanks again.
Okay, the next talk is collision-resistant functional encryption for RAMs by Prabhanjan Anand, Kai-Min Jun, Sean Leo Fang, Lo Wen Chan, and Leo is going to talk online. Are you ready, Leo?
Hello, hi.
We can hear you.
Okay, that's
yeah,
great.
Please start.
Thanks a lot for the introduction. My name is Leo. I'm here to present collision-resistant functional encryption for RAMs. This is joint work with Prabhanjan, Kai-Min, and Lo Wen. Okay. Functional encryption is a very useful primitive. It's a generalization of public key encryption, identity-based encryption, attribute-based encryption, and it's very useful to construct other powerful crypto primitives such as IO, watermarking schemes, and succinct randomized encodings. However, prior works only model the functions mainly as circuits or Turing machines. But in this paper, we focus on RAMs. So what is a RAM model? So RAM stands for random access machine. Suppose there is a huge memory starting from 1 to n, and then there is a step circuit which reads which takes the CPU state as inputs, and also one index of the memory and also the content as input. And after the processing of the step circuit, it will update the internal CPU state and output the let's address to read. So that is only for the read-only RAMs. And think about the binary search. This memory could be a very large sorted array, and you will use this CPU, the RAM, the binary search to search the memory for the desired value. And yeah, so the runtime of this binary search is only logarithmic to the size of the memory, so that's a huge benefit of the RAM program. Yeah, so FE for RAMs, the syntax is something like this. So the setup will take the public parameters as inputs, and maybe also some other parameters such as the upper bound of the runtime, and it will output the public key and also master secret key. The keygen will take the master secret key as input and also the RAM program as input. It outputs the secret key for the RAM program. The encryption will take the public key, the database, which could be very large as input, and output the ciphertext. And the decryption will take the secret key and the ciphertext and output the actual runtime of the RAM program. Actual result of the RAM program. So here we will model this decryption as a RAM program. To avoid some trivial construction, we will have this efficiency requirement, which means the runtime of the keygen is proportional to the polynomial in the size of the program, and the encryption algorithm, the runtime of the encryption algorithm is also polynomial in the size of the database. And the most important one is the decryption only is proportional to the input specific runtime instead of the worst case runtime, or it's independent of the size of the database. So that's the syntax and also the efficiency requirement we want. And for the security, we only consider selective security. So it's an interactive game between the challenger and the adversary. The challenger will set up the scheme by running the setup algorithm, and it will send the public key to the adversary. The adversary will choose a database like D0 and D1, and then send the database to the challenger, who will then pick a random bit B and then encrypt the database according to this random bit B, and then send this as a challenge ciphertext to the adversary, the CT star. And then the adversary can query the challenger as many times as he wants for the function key related to the program, as long as it satisfies the condition P to the D0 equal P to the D1, which means the output of the RAM program of the query RAM program on these two challenges database are the same. And yeah, he can do this as many times as he wants. And at the end of the security experiment, he needs to guess the random bit B chosen by the adversary. And we say the adversary wins the selective security experiment if he can guess the bit B correctly. And as I mentioned before, prior work only focus on RAM for circuits, where the decryption will depend on the circuit size. And as we know, if you convert a RAM program to a circuit, there will be a huge overhead. The size of the circuit will depend on the size of the database. So that's not desirable. That's something we don't want. And the known approaches to constructing FE for RAMs is these two work. And there is a very recent work I didn't include here. The first one is like the trivial solution. Like if you have functional encryption for circuits, and then you can convert this RAM program to circuits, and then you can use the functional encryption for circuit to construct the functional encryption for RAM. But you will have this like polynomial. So the runtime of this like approach, the decryption will depend on the small t, which is input specific runtime, and also the capital N, which is the size of the database. And if the size of the database is very large, then this is not desirable. And the second approach is by Gentry et al. In 2014. Like they show how to construct single key FE for RAMs. Yeah, so our goal in this paper is to say like whether like how can we like do this like collusion resistant FE for RAMs with succinct decryption. So succinct here means the decryption only depends on the input specific runtime of the RAM program. Okay. Yeah, the starting point is of course the gobble RAM. So gobble RAM, the syntax of the gobble RAM is something like this. So there exists a gobbling for the database, which takes the security parameter, the database, and also the upper bound on the runtime for of the runtime, which is a capital T. And it will output the gobble database that's D prime, and also the secret key, which will be used to gobble the program. The second algorithm, the gobble program, takes the secret key and also the program, it will output the gobble program P prime. And the evaluation, which is treated as a RAM program, so which means it has like random access to the gobbled database D prime, and it will take P prime as input, and it will output the P to the D, which is actual output. And so this can be treated as a one-time secret key FE for RAM. And some like normal paradigm in constructing this gobble RAM is to say like, first we construct the gobble RAM in the UMA setting, which is unprotected memory access setting. Then we upgrade it to like full security. So like we use like basically ORAN to cover the random access pattern. We use ORAN to cover the memory access pattern, and we use secret key encryption to cover the actual memory content. So that's a basic paradigm in constructing gobble RAM. And the challenge is like if we want to like go from a gobble RAM to like functional encryption for RAMs, there are some challenges in there. The first thing is like parallel reusability, like as shown by Hamlin et al. In 2019. Like this existing gobble RAMs are insecure in parallel reusability setting. They are only secure in this like a sequential reusability setting. Yeah, so maybe like we can use FE for circuits to achieve this parallel reusability, which means like it can be like run by several like decryptor in parallel, and we still can achieve security. And second part is like succinct. So for succinctness, we require the parameter should neither grow with the database length nor the worst case runtime, and the decryption time only goes like proportional to the input specific time. So we can perhaps use succinct gobble RAM, which will be used here, but it doesn't have this like parallel reusability. So our high level idea is like we can like combine this FE for circuits and also succinct gobble RAM like with some special properties to achieve FE for RAM. So that's a high level idea. Yeah, so we start from this like non-succinct gobble RAM, and yeah, and using some tricks like IO, we can get succinct gobble RAM, and then from the succinct gobble RAM, we can get the succinct and also reusable gobble RAM, and then combining this succinct reusable gobble RAM with like FE for circuit, we can get FE for RAM. So that's the roadmap to achieve this FE for RAM construction. Okay, let's start from the beginning. Yeah, so we start from the non-succinct gobble RAM, and this means the parameters in the scheme could grow with the worst case runtime of the RAM program. And for the evaluation, actually, we require the time needed. Here is like only proportional to the actual runtime of the computation, and is independent of the database. And such a scheme can be constructed from a gobble circuit, which can be constructed from one-way function. And for each step, like the blueprint for constructed this non-succinct gobble RAM is to something like this. like for each step, like we evaluate the ith gobble circuit to get the ith step of the execution for the P to the D, which is a random execution. And then we compute the recoding step, like we go from the ith output encoding to the I+1 wire labels. So through this way, we can use a gobble circuit to transit from the current step to the next step. And for full security, we can use ORAN, as I said before, to hide the memory access pattern. And we use secret key encryption to hide the memory content, basically. Okay, so like succinct, like go from a non-succinct gobble run to a succinct gobble run, we'll use like the obfuscation to delegate the execution of this non-succinct part. And succinct gobble run means like the size of the gobble program is independent of the worst case runtime T, capital T. As recorded in the last slide, like for each step, we need to generate a gobble circuit, which means the size of the gobble run depends on the upper bound of the runtime, which is capital D. So the idea here is we use an obfuscated circuit that will produce a non-succinct gobbling of the program. And then, but just obfuscating the non-succinct gobbling procedure doesn't work, since the size of the obfuscated circuit will be as large as the size of the non-succinct gobbling program. So we need some property, like we need to decompose the gobble program into many small components, such as the obfuscated circuit will only produce one component at a time. And yes, so these two properties we need here is like the first is like we can decompose the program into these small independent components. And to argue the security, we need to carry out the hybrid of the non-succinct gobbling scheme by hardwiring just a small subset of the component at a time. And by the local simulatability, we can guarantee that in each hybrid, the amount of the hardwired information is never too large, and therefore we can achieve succinctness. So that's two necessary properties to go from the non-succinct gobble run to succinct gobble run. Yeah, so like for UMA security, like so as I said before, the paradigm, like we first constructed the UMA security, then we go from the UMA security to full security. And for the UMA security, we can actually use the network in GOS 18 to satisfy. They already satisfy the two properties I mentioned before. And for full security, we need this like ORAN with strong localness, the randomness, which will be used to achieve this local simulatability. And then we use this like a time encryption. So time encryption, like at a high level, is just an encryption scheme that allows you to issue the encryption and decryption keys with scoring power as the evaluation goes on. So like a key at a time t can be decrypted anything that was encrypted under time t, but it cannot decrypt anything like upper that is larger than t. So using this like two additional components, the ORAN with strong localness, the randomness, and the time encryption, we can achieve full security. So that's for the succinct gobble run part. But the succinct gobble run itself is not going to be sufficient to construct the FE for RAMs. Like recall, like in FE for RAMs, the adversary, he can get like many functional keys as he wants, and he can do this like do this decryption in parallel. So we need this like reusable, I mean like parallel reusable gobble RAM. So this means like given this like gobble database D prime and also multiple gobble program P1 prime to PK prime, we can only learn this like P1 to the D to PK to the D, and we only learn this like output instead of like anything about the database. Yeah, so like to construct this like succinct and also reusable gobble RAM, it is like very useful to split this thing into two parts. In the first part, we need to construct this like succinct reusable gobble RAM with UMA, which is secure in the UMA setting, and note like in this like UMA setting, like essentially what we need to do is to protect the memory execution, and we do not face any like trouble in adapting the scheme, like the GOS18 scheme into the reusable setting. So the first part is easy, the UMA part is easy. And the second part is like we need to use this like UMA secure double RAN to construct a fully secure, succinct, reusable double RAN. So that's the second step. Okay, yeah, so there are some challenges in the second step. The first one is like we need to protect the memory content. So to protect the content of the memory, we need to encrypt the encryption key into our Gabble program. But however, like if we are giving out one Gabble program, we can no longer invoke the security of the encryption scheme to say that the adversary has no information about the underlying database. So since the Gabble program contains a hardware secret key. So therefore, we need to remove the encryption scheme in a hybrid, very carefully. So on a high level, the idea is to like remove the encryption scheme one by one in each hybrid. Like we start from the encryption scheme for the last Gabble program, and we just write this like junk in the database instead, and then we use the IND security to argue that this is indistinguishable from the previous the second last hybrid, and then we move from the last hybrid to the second last hybrid, and so on and so forth. Yeah, but this like the security proof doesn't work in the reusable case, since like when you try to equivocate the output or the database writes and remove the encryption key, the adversary actually like he can in principle still be able to distinguish the two distributions as like the same time encryption will appear in the other Gabble program. So that's like one issue like we need to tackle. And the second issue like is like how to protect the memory access pattern. Like we need to like somehow change the access pattern without hardwiring like too much information. So for that, we need to use the rewindable ORAN with strong localized randomness. Yeah, so like we designed this like a rewindable ORAN scheme satisfy this like strong localized randomness, which will be relying on the public key double efficient peer. Okay, so to put things together, like we show, like we can construct the FE for RAMs like this. So it is a combination of FE for circuits and also the succinct reusable Gabble RAM. So to encrypt a database D, we first use the succinct and reusable Gabble RAM to gobble the database, and then we get the D prime, which is a Gabble database and a secret key. And then we use a functional encryption for circuit to encrypt this secret key and to generate a ciphertext. And the ciphertext for the FE for RAM will be this like two components, the Gabble database D prime and the ciphertext for the functional encryption scheme for circuits. Okay, so that's the encryption part. And to generate the function key for RAM program P, we first define this circuit G to be the Gabble to be the gobbling of the program, which has a P hardwired, but will take the secret key as input, and then we generate the secret key for this newly defined circuit, and the secret key for the RAM program will be the secret key, the SK sub G. Okay, to decrypt, we first need to recover the Gabble program P prime, which will be done by using the decryption algorithm for the functional encryption for circuits. And then we can use the Gabble evaluation for the Gabble program, for the Gabble RAM to do the actual evaluation. And the security proof will we first hardwire the Gabble program, and then we use a reusable security of the Gabble RAM to argue the security proof on, I won't talk about the security proof here. Okay, so in summary, our results, we show FE for circuits plus succinct reusable Gabble RAM, then we can get FE for RAM. And compare with a trivial solution, which is the combination of FE for circuit with the RAM to circuit conversion, our work achieves the succinct in every perspective. So yeah, so that's our result. And there are many missing details in this talk, and we also show like actually you can do bounded key for bounded KFE for brands also like in our paper. Like if you are interested, please take a look at our paper. Thank you. I'm happy to take any question.
The time for question. Are there any question?
My question is, so finally you use IO in the construction, right? Can you go to the previous slide?
Yeah, like in,
yeah, no, just the
addition
second
to-
last, slide.
Yeah, so
For succinct reusable garbled RAM, I believe you're using, you need IO, is that correct?
Actually, in addition to IO, you also need the VBB obfuscation. Yeah, to achieve the rewindable ORAN with some like the strong localized randomness. So like, yeah. Yeah, so
you
like
need VBB obfuscation for which class of circuits?
For the we need VBB for the like the I guess the logarithmic depth of circuits. Yeah, since we need to use that to construct this rewindable ORAN with some special like the strong localized randomness property. Yeah, we also think about whether this is like avoidable. Yeah, but we don't know how to do it without VBB obfuscation. But as like in the FHE for RAM's paper, they also use VBB obfuscation to construct FHE for RAM. So yeah, we didn't make much progress on that front.
All right, thank you.
Thank you.
Are there any question? So is the proposal scheme is adaptively secure or selectively secure?
It's selectively secure.
Okay, so okay, I see.
Yeah, and we also don't know how to do adaptive security.
Mm-hmm. Thanks. No other question? Okay, let's thank the speaker again.
Thank you.
The last talk of this session is knowledge encryption and its applications to simulatable protocols with low round complexity by Yi Deng, Xin-Xiong Zhang, and Xin-Xiong is going to talk online.
Can you hear me?
Yeah, we can hear you.
Okay. Thank you for introduction. In this talk, I would like to present our paper. I'm Xin Zhang. It's a joint work with Yi Deng. In this talk, I will first introduce our motivations, and second, I will show the notion we put forward called knowledge encryption. Then I will present a high-level idea about how to construct knowledge encryption, and finally, I will give a simple introduction about its applications. First, let's consider the following simple protocol. Roughly, the welfare sends publicly to the approver, and the approver will encrypt its double proof, proving that it knows the secret key or some other statements. That's a toy example. And let's ignore the soundness issue here and only concentrate on simulating the approval. Now, as you can see, if the welfare doesn't know the secret key, and it can decrypt or distinguish subtext, it can't distinguish or decrypt subtext, then the simulator can encrypt domain message to conclude the simulation. And if the welfare knows the secret key, which means that it can decrypt or distinguish subtext, then the simulator can use the secret key as a trapdoor to generate the double proofs via individual extraction. However, This requires the underlying encryption scheme, satisfying that the ability of distinguishing or decrypting the ciphertext means the knowledge of the secret key. In other words, one can efficiently extract the secret key from any decryption algorithm or distinguishing algorithm. Then consider the following two encryption schemes closing to our requirements. That's witness encryption and the conditional disclosure scheme. Witness encryption allows one to use an NP instance as public key and the corresponding witness as secret key. And the CDS allows one to generate key pairs from an NP instance and its witness. Their security requires that if the instance is invalid, no efficient algorithms can decrypt or distinguish ciphertext. However, neither of them provides any security when using a valid instance. In other words, the decryption algorithm provides only a sound proof that the corresponding public key is valid. Now we have a question. Can we construct a public key encryption for which only algorithm that knows the secret key can decrypt ciphertext? In other words, the decryption algorithm provides a proof of knowledge of the secret key. Unfortunately, most of existing encryption schemes fail to satisfy this requirement without knowledge assumptions. The only exception we're aware of is a variety of Robbins encryption, of which security is based on the factoring assumption. As shown in DOM 20, this conception is useful in constructing typical security protocols, such as selective opening secure commitment and concurrent zero knowledge protocol. Well, motivated by this question, we put forward the notion of knowledge encryption. Like CDS, a knowledge encryption is associated with an NP language. The key pairs are generated from an instance and its witness. We let the public key and the secret key contain the instance X and the witness W respectively. Knowledge encryption should satisfy the witness extractability, indistinguishability, and the public key simulation properties. Witness extractability claims that if an efficient adversary can distinguish decrypt ciphertext, then there is an efficient algorithm extracting the witness, which is also part of the secret key from the adversary. This should hold even for malicious generated public key. Indistinguishability requires that for any fixed instance and its witness, no efficient algorithm can distinguish ciphertext without the secret key. And the public key simulation requires that one can efficiently simulate a public key for any valid instance without knowing its witness. In our paper, we present two constructions for knowledge encryption. The first is based on CDS and random self-reducible encryption, and the second is based on CDS only. It means that the knowledge encryption can be constructed from two-round game-based secure Bolivia's transfer, which is known from DDH, QR, or LW assumptions. Here, we only give a high-level idea about the second construction. Remind that a CDS scheme can be regarded as a special two-message secure function evaluation. It can be constructed from a two-round oblivious transfer with scheme-based security and a governing secured scheme for the secured C shown on the slides. Here, this secured takes input the instance X, witness W, and a message M, and outputs the message if and only if W is a valid witness for X. On input X and W, the key generation algorithm runs the first round of oblivious transfer to encode the witness bit by bit. It outputs X and OT messages as the public key and outputs W and the randomness used in OT as the secret key. To encrypt a message, the sender first gobbles the secret and sends the gobbled secret and the corresponding labels for X and M directly, and sends the labels for W via OT protocols. Finally, by retrieving the labels for W from OT, and evaluating the garbled circuit, one can obtain the message encrypted. So to construct a knowledge encryption scheme, we embed a simple decoding mechanism in the secure C. As shown on the slide, C has an extra input Y, and Y equals all zero string. C works in the same manner as before. When Y doesn't equal all zero string and W is a valid witness, C outputs the sum of Y, WI. We modify the encryption and decryption algorithms naturally. Note that the honest encryption algorithm always chooses Y as all zero string. Here we only present a high-level idea about the witness extractability property of this construction. A key observation here is that, as shown on the slide, when choose Y as a string of 0, except the J's position, the result subtext will be indistinguishable from the encryption of J's position of witness. So an extractor can extract the complete witness bit by bit by checking that in the view of adversary, this subtext is closer to the subtext of which bit. We refer to our paper for more details. Now, as shown on the slides, knowledge encryption is useful in the construction of the first 3 round T-epsilon simulatable oblivious transfer and lots of other protocols achieving T-epsilon security, such as delayed input zero knowledge argument and two-party computation for independent input function analysis. And here we only present a simple introduction about the first construction, and we refer to our paper for more details about other constructions. A various transfer is a protocol between a sender holding 2 messages and a receiver holding a choice bit. At the end of the protocol, the receiver should learn the message of his choice, but learn nothing about the other message. The sender, on the other hand, should learn nothing about the receiver's choice bit. Using knowledge encryption, we construct the first 3 round T-epsilon simulatable oblivious transfer, satisfying the full simulatable security for the receiver and the T-epsilon simulatable security for the sender. Our construction relies on the techniques including Weyman construction and individual reductions put forward by them. A natural idea here is to have the receiver generate a pair of public keys, pick0 and pick1 of knowledge encryption from 2 NP instances, x0 and x1. And the receiver knows witnesses for one and only one of these 2 instances. And so that it can receive one and only one message encrypted by the sender. Here among these 2 public keys, one public key is generated using the key generation algorithm, and the other is generated using the public key simulator. Then for the sender, it doesn't know which one is simulated. Therefore, it doesn't know the input bit B of the receiver. Now, there are 2 major challenges. First, we need to make sure that the receiver knows a witness for only one of these 2 instances. And second, the simulator needs to extract the input of the adversaries. To solve the first challenge, we require the sender to generate and send a hard NP instance Y, and the receiver uses the Sigma protocol to generate these 2 instances, X0 and X1. Remember that a Sigma protocol is a 3-round public coin protocol satisfying the special soundness and the special honest welfare zero knowledge properties. The special soundness property requires that given 2 acceptable proofs with the same first round message and different challenges, one can efficiently extract the witness for the instance. And the special honest welfare zero knowledge property requires that given challenge E, it's easy to compute an accepting transcript which is indistinguishable from an honest one. Now go back to our construction. Give me Y and input B. The receiver prepares two instances X0 and X1 in the following way. It first generates a random challenge EB and runs the honest welfare zero knowledge simulator to obtain an acceptable proof AEBC for Y. It chooses another random challenge if Y must be not equaling to EB and sets instances xi in the form of YAEI. We call xi a yes instance if and only if there is a string z such that AEIZ is an acceptable proof for Y. And from the special soundness of Sigma protocol, without the witness of Y, anyone cannot generate two acceptable proofs with the same first round message but different challenges. Therefore, the receiver knows witnesses for only one of X0 and X1. As for the choice of Y, in our paper, we let Y equals Y0, Y1, where Y0 and Y1 are images of a one-way function F. Y is said to be a yes instance if there is R such that FR equals Y0 or FR equals Y1. And finally, the sender proves to the receiver that it knows one prime image of Y0 or Y1 by a WI protocol satisfying special soundness. This step is used for the following security proof. To simulate the receiver, roughly the simulator first extracts a witness for Y from the WI protocol by rewinding. Then it can generate two yes instances, X0, X1, and therefore to validate the public keys, PK1, PK0, PK1 with their secret keys. When receiving the two ciphertexts from the sender, it can decrypt to obtain both messages and send them to the functionality to conclude the simulation. From the fact that a simulated public key is indistinguishable from an honest one, the messages extracted by the simulator in the ideal world are indistinguishable from the output of the receiver in the real world. Remember that that's a non-traditional extraction strategy. The simulator obtains message by decrypting rather than rewinding. To simulate the sender, the simulator needs to extract the input bit of the malicious receiver. Here we will use the individual reduction technique put forward in DEN 20. Roughly, this technique shows that for any R star, there is a good extractor E outperforms all other algorithms in extracting secret keys or witnesses. The simulator runs this nearly optimal extractor E to extract the secret key, or in other words, the witness of the instance on KE public keys generated by the malicious receiver. According to the result of extraction, the simulator runs in different manners. In the case that it succeeds to extract only one witness, WB prime, the simulator sets B equals B prime and sends it to the OT of OT functionality. After obtaining the message MB, the simulator encrypts it using both public keys, respectively, to conclude the simulation. In the case that it fails to extract any secret key, the simulator just sets B equals 0 and continues. And if it succeeds to extract both secret keys, then the simulator just aborts. Now, in the first case, it means that the adversary can only decrypt the ciphertext under the public key PKB. Otherwise, suppose the adversary can distinguish the ciphertext under public key PK1 minus B. Then from the witness extractability of knowledge encryption, there is an efficient algorithm extracting WE1 minus B, breaking the optimality property of the extractor. Therefore, remember that the only difference between an ideal execution and a real one in this case is the message encrypted using PK1 minus B. The adversary cannot distinguish them. In the second case, It means that the adultery cannot describe or distinguish both subtexts. Following a similar analysis with the first case, it's easy to show that the simulator can successfully conclude the simulation in this case. And in the third case, if it extracts two witnesses, then from the special signage of sigma protocol, one can efficiently extract a preimage of Y0 or Y1, which is infeasible from the fact that A prime, E prime, D prime is a witness hiding. Therefore, the simulator will succeed in all these cases. In other words, no matter which strategy the adversary chooses, the simulator will always win. That's a win-win structure. At the end, we present a summary of our paper. In our paper, we first introduced the notion of knowledge encryption and present its definition. Then we present two constructions for knowledge encryption, which shows that knowledge encryption can be conducted from any two-round game-based oblivious transfer. And finally, we present some applications of knowledge encryption, including the first three-round typical simulatable oblivious transfer and a variety of protocols achieving typical simulatable security, which outperform prior works in either relying assumption or security. That's all. Thank you for your attention.
Are there any questions? So knowledge encryption is very similar to extractable witness encryption, but the difference is knowledge encryption has key generation phase. Is right? Is it right?
Yes, the knowledge encryption will have an actual key generation algorithm, and it rely better assumptions than extractable witness encryption.
Okay, so on the does extractable witness encryption imply knowledge encryption? Is there any relationship between extractable witness encryption and knowledge encryption?
Well, extractable witness encryption are very close to the knowledge encryption, except the indistinguishability properties. And in some cases, you can use extractable witness encryption as a replacement. And the main idea of our paper is to conduct low-round complexity protocols with more standard assumptions such as TDH or QR. And I think extractable witness encryption is hard to conduct from these assumptions.
Thanks. Are there any questions? No? Okay, thanks to speak again. This is the end of this session, and we have lunch break.